Welcome to the fascinating world of modern physics. In this chapter, we'll explore the groundbreaking ideas that have revolutionized our understanding of the universe. Modern physics is a branch of science that emerged in the early 20th century, challenging the classical views that dominate for centuries. Unlike classical physics, which deals with everyday phenomena at familiar speeds and sizes, modern physics delves into the mysteries of the very small, the very fast, and the very massive. Get ready to journey through concepts like quantum mechanics, relativity, and the structure of the cosmos, all of which have shaped the technology and knowledge we rely on today. Modern physics differs from classical physics in several key ways. While classical physics, such as Newtonian mechanics, explains the motion of everyday objects, modern physics addresses phenomena that classical theories cannot. For example, it explains the behavior of particles at atomic and subatomic scales and the effects of objects moving close to the speed of light. These new theories, including quantum mechanics and relativity, have led to discoveries that classical physics could not predict, such as the dual nature of light and the warping of spacetime. This shift has opened up entirely new fields of research and technology. Quantum mechanics is one of the cornerstones of modern physics. It describes the strange and fascinating behavior of matter and energy at the smallest scales, atoms and subatomic particles. Unlike classical physics, quantum mechanics introduces the idea that particles can exist in multiple states at once and that their properties are fundamentally probabilistic. This means we can only predict the likelihood of finding a particle in a particular state, not its exact position or momentum. Quantum mechanics has led to revolutionary technologies like lasers, semiconductors, and MRI machines, making it a vital part of our modern world. One of the most surprising discoveries in modern physics is the principle of wave-particle duality. This concept reveals that particles like electrons and photons can behave both as particles and as waves, depending on how they are observed. For example, light can form interference patterns like waves, but also knock electrons off metal surfaces like particles. This duality challenges our everyday intuition and shows that the nature of reality at the quantum level is far more complex than previously thought. Understanding wave-particle duality is essential for grasping the foundations of quantum mechanics. Heisenberg's uncertainty principle is a fundamental concept in quantum mechanics. It states that it is impossible to know both the exact position and momentum of a particle at the same time. The more precisely we measure one, the less precisely we can know the other. This isn't just a limitation of our measuring tools, it's a fundamental property of nature. The uncertainty principle has profound implications for how we understand the behavior of particles and the limits of human knowledge at the quantum scale. Atoms are the basic building blocks of matter, and understanding their structure is crucial in modern physics. Each atom consists of a nucleus made up of protons and neutrons, surrounded by a cloud of electrons. The arrangement and behavior of these components determine the properties of elements and how they interact. Modern physics has revealed that the nucleus itself is held together by powerful forces, and the electrons occupy specific energy levels, leading to the unique characteristics of each atom. Bohr model of the atom was a major step forward in understanding atomic structure. According to this model, electrons orbit the nucleus in specific energy levels. When electrons jump between these levels, they absorb or emit energy in the form of light, creating atomic spectra. These spectra are like fingerprints for each element, allowing scientists to identify substances and study their properties. The Bohr model paved the way for quantum mechanics and remains a key concept in modern physics. Nuclear physics explores the structure and behavior of atomic nuclei. It investigates the forces that hold protons and neutrons together, as well as the processes that can change one element into another. This field has led to the development of nuclear energy, medical imaging, and treatments for cancer. Nuclear physics also helps us understand the origins of elements in the universe and the powerful reactions that fuel stars. Nuclear fission and fusion are two processes that release enormous amounts of energy from atomic nuclei. Fission occurs when a heavy nucleus splits into smaller parts, releasing energy and more neutrons. This process powers nuclear reactors and atomic bombs. Fusion, on the other hand, combines light nuclei to form a heavier nucleus, as happens in the Sun. Fusion promises a nearly limitless source of clean energy if it can be controlled on Earth. Both processes are central to nuclear physics and have significant technological and societal impacts. Radioactivity is the spontaneous emission of particles or energy from unstable atomic nuclei. There are three main types: alpha, beta, and gamma radiation. Each type involves different particles and energy levels, and they have various effects on matter. Radioactivity is used in medicine, industry, and scientific research, but it also poses health risks if not properly managed. Understanding radioactivity is essential for harnessing its benefits and minimizing its danger. Isotopes are atoms of the same element with different numbers of neutrons. They have a wide range of applications in medicine and industry. In medicine, radioactive isotopes are used for imaging, diagnosis, and treatment, such as in PET scans and cancer therapy. In industry, isotopes help in tracing processes, inspecting materials, and measuring thickness. Their unique properties make isotopes invaluable tools across many fields. Particle accelerators are powerful machines that speed up charged particles to high energies and smash them together. These collisions allow scientists to probe the fundamental building blocks of matter and discover new particles. Particle accelerators have led to major breakthroughs, such as the discovery of the Higgs boson. They also have practical uses in medicine, industry, and materials science, making them essential tools in modern physics research. Higgs boson is a fundamental particle discovered in 2012 at the Large Hadron Collider. It is associated with the Higgs field, which gives mass to other elementary particles. The discovery of the Higgs boson confirmed a key part of the Standard Model of particle physics and deepened our understanding of how the universe works at its most basic level. This breakthrough was the result of decades of research and international collaboration. Relativity is a revolutionary theory developed by Albert Einstein. It consists of two parts: special relativity and general relativity. Special relativity deals with objects moving at constant speeds, especially those close to the speed of light, and introduces concepts like time dilation and length contraction. General relativity goes further, describing gravity not as a force, but as the curvature of spacetime caused by mass and energy. These ideas have transformed our understanding of space, time, and gravity. General relativity explains gravity as the warping of spacetime by mass and energy. Massive objects like planets and stars bend the fabric of spacetime, causing other objects to move along curved paths. This theory has been confirmed by observations such as the bending of light around massive bodies and the precise orbits of planets. General relativity is essential for understanding phenomena like black holes and the expansion of the universe. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse at the end of their life cycles. Black holes have fascinating properties such as event horizons and singularities, and they play a key role in the evolution of galaxies. Studying black holes helps scientists test the limits of general relativity and explore the most extreme environments in the universe. Dark matter and dark energy are two of the biggest mysteries in modern physics. Dark matter is invisible and does not emit light, but its gravitational effects are seen in galaxies and clusters. Dark energy, on the other hand, is driving the accelerated expansion of the universe. Together, they make up about 95% of the universe's total mass and energy, yet their true nature remains unknown. Unlocking these secrets is a major goal of current research. Cosmology is the study of the universe as a whole, its origins, structure, evolution, and fate. The Big Bang Theory is the leading explanation for how the universe began, suggesting it started from an extremely hot and dense state and has been expanding ever since. Evidence for the Big Bang includes the cosmic microwave background radiation and the observed expansion of galaxies. Cosmology combines physics, astronomy, and mathematics to answer some of humanity's biggest questions. Scientists use a variety of tools and methods to study the origins and evolution of the universe. Telescopes, satellites, and space probes collect data from distant stars and galaxies. Particle detectors and accelerators help us understand the fundamental particles and forces at work. By combining observations with theoretical models, researchers can piece together the history of the cosmos and predict its future. This ongoing quest drives much of modern physics research. Modern physics has transformed technology in countless ways. Quantum mechanics led to the development of transistors, lasers, and computers. Nuclear physics enabled medical imaging and cancer treatments. Relativity is essential for GPS systems and satellite communications. These advances have improved our quality of life, revolutionized industries, and opened up new possibilities for the future. The impact of modern physics is felt in nearly every aspect of our daily life. With great power comes great responsibility. The discoveries and technologies of modern physics raise important ethical and environmental questions. For example, nuclear energy offers clean power but also poses risks of accidents and waste. Particle accelerators and research facilities require significant resources. Scientists must consider the potential impacts of their work on society and the environment, balancing progress with safety and sustainability. Modern physics research can have significant environmental impacts. Nuclear waste, energy consumption, and the use of rare materials are just a few of the challenges. Scientists and engineers are working to develop safer, more sustainable technologies such as fusion power and renewable energy sources. Environmental stewardship is becoming an integral part of scientific research, ensuring that progress benefits both humanity and the planet. Quantum computing is an exciting application of quantum mechanics. Unlike traditional computers, which use bits, quantum computers use quantum bits or qubits. These can exist in multiple states simultaneously, allowing quantum computers to solve certain problems much faster than classical computers. Quantum computing holds promise for breakthroughs in cryptography, materials science, and artificial intelligence, potentially transforming entire industry. Lasers are a direct result of quantum physics. They produce highly focused beams of light with many uses, from surgery and manufacturing to communications and entertainment. Photonics, the science of light, is a rapidly growing field that relies on quantum principles to develop new technologies. These advances are making our devices faster, more efficient, and more precise. Modern physics has revolutionized medical imaging. Techniques like MRI, PET scans, and CT scans rely on principles from quantum mechanics and nuclear physics. These technologies allow doctors to see inside the human body without surgery, leading to earlier diagnoses and better treatments. The ongoing development of imaging technology continues to improve healthcare outcomes worldwide. Development of semiconductors is rooted in quantum physics. Semiconductors are materials that control the flow of electricity in devices like computers, smartphones, and solar panels. Understanding how electrons behave in these materials has led to the creation of transistors and integrated circuits, which are the foundation of modern electronics. This technology powers the digital world we live in today. Global Positioning System, GPS, technology relies on the principles of relativity. Satellites orbiting Earth experience time differently than clocks on the ground due to both special and general relativity. Without correcting for these effects, GPS systems would quickly become inaccurate. This is a real-world example of how modern physics directly impacts our daily lives, enabling navigation and location services worldwide. Fusion energy is often called the holy grail of clean power. By mimicking the processes that power the sun, scientists hope to create reactors that provide abundant, safe, and sustainable energy. Fusion produces no greenhouse gases and has minimal radioactive waste compared to fission. While technical challenges remain, progress in fusion research could transform the world's energy landscape in the coming decades. Despite its successes, modern physics still has unanswered questions. Scientists are searching for new theories that go beyond the standard model, hoping to explain phenomena like dark matter, dark energy, and the unification of forces. Experiments at particle accelerators and observatories around the world are pushing the boundaries of knowledge, seeking to uncover the next big breakthroughs in our understanding of the universe. Modern physics has transformed our view of the universe, from the tiniest particles to the vastness of space. Its theories and discoveries have led to technological revolutions and deepened our understanding of nature. As we continue to explore the unknown, modern physics will remain at the forefront of scientific progress, inspiring new generations to ask bold questions and seek innovative solutions. The journey is far from over, and the future holds endless possibility.